This video is about RC time constants. It corresponds to section 11.4 of Applied Analog Electronics. Now, RC time constants occur all the time in electronics. Whenever we're dealing with filters, later on when we deal with our hysteresis oscillator, we're going to be looking at RC time constants. And it helps to look at sort of the classic physics example from which the notion of RC time constants comes. And this is that classic physics example. We've got a capacitor, and initially we have it charged to a voltage V0. Then at time 0, we press the switch and connect it through a resistor to a different voltage, call it V infinity. And the question is, what is the mathematical formula for the voltage on the capacitor as a function of time? And we're going to do it from first principles. So let's start by looking at the capacitor and saying the charge, which is a function of time, is the capacitance times the voltage, which is a function of time. Okay, so this is the capacitor C, and I won't bother drawing the switch. I will just do the resistor and the voltage source. So we have a resistor here, and we'll have a current. And that current is charging that capacitor. Well, there's two things we know about the current. One, since it's charging the capacitor, it's the derivative of the charge with respect to time. That's what current is it's how much the charge is changing. We also have, however, Ohm's law about what's happening on this resistor here, and that says that V infinity minus V of t, that's the voltage across the resistor in that direction, divided by the resistance is going to be I. Okay, so we can put all these things together. We can say, okay, that's I of t, so make them all functions of time. The resistance is not a function of time. If we combine these things, we get that V infinity minus V of t over R equals, derivative here, C dV dt. All right, and we can simplify that a little bit to get V infinity minus V of t equals RC dV dt. That's a simple first-order differential equation. And though it's beyond the scope of this class to show you how to solve differential equations like this, this is one of the easiest differential equations to solve. And we get as a solution that V of t minus V infinity equals V0 minus V infinity times e to the minus t over RC. So this is an exponential decay here, and we can check the endpoints. At t equals 0, e to the 0 is just 1, so we have V0 minus V infinity equals V of t minus V infinity, which is just to say that at time 0, V of 0 is V sub 0. That's why we named it that. And if we take t out to infinity, then we have e to the minus infinity is just 0, so this thing on this side just disappears, becomes 0. And we have that V at time infinity minus V infinity equals 0, or just V infinity is the voltage when we get to infinity. So this thing is going to be an exponential curve that starts at time 0 being V0 and decays towards V infinity. Let's take a look at what that looks like. All right, we have got an RC charging curve here. At time 0, we're at v0, and as time progresses, we get closer and closer to v sub infinity. Now, the same curve we get for either charging or discharging. It just depends whether v0 or v infinity is the larger number. So there isn't anything about having to go to 0 or anything like that. We're going from v0 initially to an asymptotic value of v infinity. All right, you can see something else on this plot, and that is I've got something labeled rise equals 2.197 microseconds. What that's referring to is the way that engineers measure how fast a transition like this happens. Obviously, we can't say how long does it take to get to v infinity, because that is an infinite amount of time, and that wouldn't be a very useful piece of information about how fast it's moving. It's always infinity. So instead, what people do is they say, how long does it take to get from 10% of the way to 90% of the way? And that's the rise time. 10% and 90% were kind of arbitrary choices, but they're the ones that classically have been used. All right, how do we think about this? How do we get a computation for what is the rise time? Well, perhaps the easiest thing to do is to go back to that equation we just had and to normalize the voltages. And what we want to do is normalize the voltages so that V0 is going to be 0 and V infinity is going to be 1. So this is what fraction of the step we're going. We're going from 0.1 to 0.9 of that on that normalized voltage. So how do we do the normalization? Well, the simplest way is to say we want V0 minus V of t. Well, at time 0 we want that to be 0. And at time infinity we want it to be 1. So V0 minus Vt over V0 minus V infinity is our normalized voltage. But if you look at what we have there, that's very similar to the formula we have here. It's just that we have V0 minus Vt instead of Vt minus V infinity. Well, you can take that by taking V0 minus V infinity minus the Vt minus V infinity to get this number. So this becomes just 1 minus e to the minus t over rc. So this is our normalized function. So whenever we're doing a step of any sort, it's going to be starting at 0 and going to 1 on this normalized voltage. So this is a way to get rid of those what are the two voltages and just say how much of the step are we making. And so we're interested in knowing how long it takes this thing to go from 0.1 to 0.9. All right, and we can do this, we can turn this thing around and say, all right, if this is going to be, say this is the fraction of the way we're going, then we're going to have t is minus rc times the natural log of 1 minus f. Okay, just rearranging this, taking 1 minus f to get rid of the 1 on that side, taking the natural log, dividing by multiplying by rc. Okay, and then it's a fairly simple piece of math to say, well, the rise time is just going to be minus rc natural log of 1 minus 0.9 minus, and then I'm going to have minus rc times the natural log of 1 minus 0.1. And you notice that everything in here is constants except for the rc, so I'm going to get this thing is equal to approximately, what would it be? RC times about 2.197. Get out a calculator to do that if you want. And so the rise time is about 2.2 RC time constants. So you can look at rise time and the RC time constant for the curve as being different ways of looking at how fast is a transition happening. The reason the engineers often use rise time rather than just giving an RC time constant is sometimes the transition that's being made doesn't have a nice, simple, exponential RC time constant sort of charging curve. Sometimes it's a different shape because the current isn't a simple relationship the way it is for the RC time constants. So the 10%, 90% can be applied to any sort of transition, whereas RC time constants really only apply to these simple single exponentials. The single exponentials are common enough that it's worth thinking about them a lot of the time. Okay, I think that's all we really need to have right now on RC time constants. So that's it for this video.